This question is from the textbook from A levels year 2 pure to mathematics. Topic is differentiation, and this is exercise 9A, question number 10. The question asks us to prove from first principles that the derivative of sin x is cos x. So we start by understanding what is meant by first principle. Let's assume we have a curve here, and when we have a point with x as the x coordinate on the curve, hence the y coordinate of this point will be f of x. If we move x steps away, h steps away horizontally, and we have another point h steps away, the x coordinate here will be x plus h, and the y coordinates are going to be f of x plus h. If I want to find the gradient of this line that connects these 2 points, I can use the gradient formula y2 minus y1 divided by x2 minus x1. Now, if I keep reducing the distance h between these 2 points, or if I say that if h tends to 0, then this line becomes smaller and smaller, and the point x plus h, comma f of x plus h keeps on getting closer and closer to this point here. So when this line becomes smaller and smaller, then the gradient of this line becomes closer and closer to gradient of the tangent at x. We are going to use the same concept again. Let's assume we have a point with the x coordinate as x and the y coordinate as sin x. If we move h distance away horizontally, and we have another point at a distance of h units away, the x coordinate of this point is going to be x plus h, and the y coordinate of this point is going to be f of x plus h or sin x plus h. So once again, if we find the gradient of the line connecting these 2 points, we use the formula y2 minus y1 divided by x2 minus x1. So we have y2 minus y1 divided by x2 minus x1. Now, as the distance h tends to 0, this point keeps coming closer and closer and closer to the point x. And as the distance gets lesser, or as h tends to 0, the gradient of this line gets closer and closer to the gradient of the tangent drawn at x. So we use this. So we say limit as h tends to 0. So we have y2 minus y1, so sine of x plus h minus sin x divided by x2 minus x1, which is x plus h minus x. So x and x minus x cancel out. We can expand sine of x plus h using the formula. We have sine of a plus b here. Let's expand this. So sine of a plus b gives sine a cos b plus cos a sin b. Therefore, we have limit as h tends to 0. We expand the formula, so we have sine x cos h plus cos x sin h minus sin x, all divided by x. We can bring the terms containing sin x together. So we have sin x and minus sin x. So limit as h tends to 0. All this is only happening because the gradient of the tangent is getting closer, or rather gradient of this line is getting closer to the gradient of the tangent when h tends to 0. Therefore, we write this in every step. So we have the two terms containing sin x written together, sin x cos h minus sin x all divided by h plus cos x sin h all divided by h. So we pull out or factorize by removing sin x common. So sin x into cos h minus 1 divided by h plus, we pull out cos x here, cos x into sin of h divided by h. Now let's understand what happens here. We have h tending to 0, or value of h getting closer to 0. So cos of 0, so this h here tends to 0. So let's see what is cos 0. So cos of 0 is 1. So technically in this place we have 1. So 1 minus 1 gives us 0. So 0 divided by anything gives us 0. So here we have sine of x into 0. Sine x into 0, which technically gives us 0. So we can just write a 0 here for this entire term. Alright. So limit as h tends to 0. So this entire term turns to 0 because I have 1 minus 1 here. So this makes the numerator here 0 divided by h. And that whole thing multiplied by sine x gives 0. So we have 0 here. And then for this one, as h tends to 0, so sine of 0 will give us 0. So sine of 0 gives us 0. So this is not exactly 0, but it tends to 0. But both values are extremely negligible, so they can cancel out. So we are left with just cos x. And that's our required answer.